So going back to our example, our hypotheses are the null is that mu equals 191. The alternative is that mu is greater than 191. So that we see we have a one-tailed test, and specifically we have a right-tailed test. And then here's our sample data. The sample mean was 197.1. Sample standard deviation is 25.6, and we have a sample size of 100. Now let's make an observation. This observed sample mean of 197.1 is larger than expected if the null hypothesis is a true statement. Now, these two hypotheses we could think of as competing mathematical statements. For the sake of argument, we're going to assume that the null hypothesis is a true statement. And then we're going to ask ourselves, well, if that were true, what's the probability of observing a sample mean as big as what I got? Okay. So that's the question that we want to ask. What's the probability of observing a sample mean at least as large as 197.1, assuming the null hypothesis is true? Again, we're going to assume that our null hypothesis is a true statement, and we're going to calculate a probability of observing a sample mean at least as large as what we observed. And then if that probability is small, this can indicate that maybe my assumption is not a true statement. However, if we get a relatively large probability, then that's an indication that maybe my assumption is a true statement. Okay. And so the theoretical details behind the calculations of this probability we're not going to get into here in this lesson. We're going to let you can read a little bit about the details in the book, but let's just focus on understanding what we're going to focus on in these lessons is understanding what it is we're doing and what it all means. We're going to let the workbook do all of the calculations, and we're going to let the book explain the details. We're just going to focus on, again, understanding what it is we're doing and what it all means. So in this example, here are our hypotheses. Here's our sample data. So if we go to the workbook chapter 7 and the worksheet mean, we're going to see something similar to what we've seen before. Some yellow cells that we can change and some green cells that are automatically calculated. So in these yellow cells, we're going to enter our information from our hypotheses and from our data. So mu naught is the number that appears in the null hypothesis. So we see the number 191. So we're going to enter that here in this cell. X bar, that's our sample mean, 197.1. S is our sample standard deviation. N is our sample size. And then number of tails is the number of tails in our test. This is a right-tailed test, which is has one tail. So we enter 1 here. Now the worksheet automatically calculates this so-called test statistic, and then it calculates this p-value. And so this p-value is 0.0086. So what does that p-value mean? Well, informally, the p-value is the probability of observing a sample mean at least as large as the one observed, assuming that the null hypothesis is a true statement. All of these calculations are based on the assumption that the null hypothesis is a true statement. Okay. So what does this p-value mean? Well, if the p-value is small, then the observed sample mean is very unusual, assuming the null hypothesis is true. So if we get a small p-value, then we should reject the assumption. So we're going to assume that something is true, calculate the probability of observing something that we already observed, and if that probability is small, then that's an indication that our assumption is probably incorrect, and so we're going to reject it. On the other hand, if that probability is large, then that's an indication that our assumption may not be incorrect, and so we should not reject it. So now we use this word small, but then the next question is, well, just how small does that p-value have to be? Do we need a p-value of 0.0001, or is 0.1 okay, or is 0.25 okay? So just how small does that p-value have to be? So the cutoff value for a small p-value is denoted alpha, and we call that the significance level. Now we could use any significance level that we want. The most common value is 0.05, and that's the only number that we're going to use in this book, or in this class. But other books, other classes, we could use other values like 0.01, 0.1, 0.2, but we're going to use 0.05. Now associated with the significance level is a number called the confidence level, and it's the number 100 times 1 minus alpha percent. And so if we use a 0.05 significance level, that corresponds to a 95% confidence level. And I think our book always uses the term significance level, but other books could use the term confidence level. But they mean essentially the same thing. The confidence level is just 1 minus the significance level. Now here's our criteria that we're going to use to interpret our p-value. If the p-value is less than alpha, then we say we reject the assumption of the null hypothesis. If the p-value is greater than alpha, then we do not reject the null hypothesis. So this is always the criteria that we're going to use in all of our hypothesis tests. The p-values are going to be calculated in different ways, but interpreting them is going to be the same. If the p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than alpha, then we do not reject the null hypothesis. So in this particular example, we have a p-value of 0.0086. We compare that to the number 0.05. P-value is less than 0.05. And so we would say that we reject the null hypothesis in favor of the alternative hypothesis. So again, we kind of think of this null and this alternative as competing statements. If we reject the null hypothesis, then that means that we favor the alternative hypothesis. And so our final conclusion here is that the alternative hypothesis is really the same as the researcher's claim. And so we reject the null hypothesis. We're kind of saying to some extent that the alternative is a true statement. But saying that that's a true statement, that's kind of more a little bit stronger statement than we want to make. So our final conclusion is going to be that the data support the claim that the mean weight of all men in the United States has increased from the year 2002 to the year 2006. So the data support the claim. We don't say that the claim is true. We don't ever say that the claim is that we prove the claim. We never prove or disprove anything with statistics. We support claims. We do not support claims. That's as strong as our final statement is going to be. So there we go. Our sample data appeared to support the claim, and our hypothesis tells us that the support is strong enough for us to conclude that the data do indeed support the claim. So that's the basic steps in hypothesis testing. Just kind of one way of restating our final conclusion is we might say that the mean weight has significantly increased from 2002 to 2006. This is just another way of stating our final conclusion. Statisticians like to use this word significantly, and so this is just a way of stating our claim or our conclusion in terms of that word, significantly. Now let's look at another example. This is example 7.1 from the book. It's going to be a similar type scenario. We're just going to have some different numbers involved here. So in the year 2002, Americans paid an average of $3,302 per year on health care and prescription drugs. Now exactly where did this number 3,302 come from? We won't worry too much about that. We'll just take that number for granted. Okay. So now an investigator claims that in the year 2005, average expenditures are lower. So we're comparing the average or the mean amount in 2005 to this number 3,302. So in order to test this claim with 100% certainty, we'd have to go out and survey every single person in the United States in the year 2005, add up all their expenditures, divide by the total number of people, and that would give us our population mean. If that population mean were less than 3,302, then our claim would be true. But we obviously can't do that. So instead, we went out and we surveyed 100 people from the year 2000, or in the year 2005. We asked each one of them, what's your healthcare and prescription drugs costs? And we got a mean of $3,190 and a standard deviation of $980. Now our data here appear to support the claim because this number here is less than 3,302. But again, this data do not prove the claim is true. This number here of 3,190 is an estimate of the population mean. We want to determine just how strong do this data support the claim. Okay. So the first step is to define the parameter. So what we're making a claim about is the average expenditures in 2005. So we're going to note that mu is the mean healthcare and prescription drug costs of all Americans in 2005. Now when we define the parameter, we always use this word all, and that's to stress the fact that we're making a claim about the population of all Americans in 2005, not just the 100 people in our sample. We're interested in more than just this sample of 100 people. We're interested in this population of all Americans. Okay. So now we need to set up our hypotheses. Well, remember, our null hypothesis is the statement of no change or no difference. So if there were no change, then mu would equal 3,302. That's the amount in 2002. So our null hypothesis is going to be the statement that mu equals 3,302. Okay. Now the claim is that in 2005 average expenditures are lower than they were in 2002. So our alternative hypothesis, the same as the claim, is that mu is less than 3,302. So we see that we have a left-tailed test or just a generic one-tailed test. Okay. And so the test that we're using here to test this claim is what we call the Z or the T test. We'll talk about the difference between these two tests here in a bit. But here again, here's our hypothesis for this particular example. Here's our sample data. And so we're going to go to our worksheet here and enter our information. Here's the number in the null hypothesis, our sample statistics. This is a one-tail test. Here's our test statistic, and here's our p-value. This is the most important number in all these calculations, the p-value. So now we're going to interpret this p-value in the same way as we did in the previous example. We're going to compare this p-value to the number 0.05. In this case, the p-value is greater than 0.05, and so our conclusion is to not reject the null hypothesis. So we don't favor the alternative hypothesis in this case, and so our conclusion here would be that the data do not support the claim. Our data appeared to support the claim, but our hypothesis test tells us that the strength of that support was not high enough or not strong enough for us to conclude that the data do support the claim. Okay. So in other words, we could say that there is not a significant decrease in the average expenditures. There just doesn't appear to be that much difference or that much decrease in the expenditures from the year 2002 to 2005.